here is the basic concepts of chromatography, and once you understand the basic concepts, then it don't matter what GC you're working on. They're all basically, then you just got to learn the button pushing, because they're all going to be doing the same thing. And in this case, for our example, I'm doing a Siemens Maxim 2 and just showing kind of the oven ways, but you got your electronics at the top, same thing with the Yokogawa, same thing with the PGC 5000, ABB, it don't matter. We're gonna have a mezzanine in the middle, and that is if we need to mount a flame ionization detector. TCDs will always be in the oven, and that is for a purpose that we'll get to in 1 second here. But the FID, it'll be located in the mezzanine because it's gonna have a little tube coming out. And this right here, if you got FIDs, do y'all have any FIDs? Flame ionization detectors?
We have FPDs.
So you have sulfurs. So you're looking for sulfurs with an FPD. So FID, and we'll go ahead and make this one an FPD, flame photometric detector. Flame photometric detector, FPD. So FPDs are the same concept. You got a flame inside of there, and you're looking for sulfurs. Sulfurs are going to put off a specific light value that we'll get into in just a second here. And then thermal conductivity detectors, which is classic, and they are not going anywhere, and they're getting more and more reliable. Matter of fact, they're starting to get rid of FPDs and just going straight to TCDs, because you can do ppm level with TCDs nowadays easily. So kind of heading that direction. We're going to have columns in our oven. Our oven is going to have our carrier gas coming in. We're going to have sample valves, and this is going to be our sample coming in with an SSO, and then our sample going out with an ARV. Do you know why we have to have an SSO and an ARV? Sample shutoff valve will stop the flow of sample coming in, and then the ARV is going to atmospheric reference vent the sample. Why do we have to do this? We have to do this because gases can be compressed. If you have a back pressure building up here and then it relieves and then you get back pressure, you're going to have a different size sample every time because you can compress gases. You're going to have a different size sample every time. You're not going to be accurate. You have to have the same size sample every time. So what we do in all GCs, Yokogawa's vent for 10 seconds, ABBs, I'm not for sure how long y'all vent, Maxim's 8 seconds, but you're going to stop the sample, vent to atmospheric pressure for 8 seconds on this one, and then you inject. That way you have the same size sample every single time. Due to gases being compressed, we are going to vent to atmosphere and get the same size sample. That is a constant. Constant. GCs are built on constant. Next constant that we are going to have is our oven temperature. A very, very typical oven temperature is going to be 140 degrees F. Do you know what that is in centigrade?
40.
60. 60. This is a very, very common temperature that we use for an oven temperature because it keeps everybody in their vapor state that typically we will be using, unless you're dealing with some toluenes or super big heavy stuff, then you're going to need to get that temperature way up there a little bit higher. But for a typical refinery and such like this, we're going to go 140 F, 60 degrees Celsius for an oven temperature. Those are another two temperatures that you need to remember for the rest of your life. Just this is separate, but 40 degrees F is 4 degrees C. Where do you see that at? Chillers. Absolutely. For your sims, you're going to knock out moisture. And this drops everybody below their dew point. And when you drop them below their dew point, then they liquefy up. And when they drop out the bottom, peristaltic pump kicks them out and stuff like that. 40 degrees Fahrenheit is 4 degrees Celsius, and that will knock your moisture out. So I don't know about here because it's a little bit drier, but in Houston area, you take a beer, you set it down on the table, sweat just pours off of it because we have so much humidity in the air. It's not even funny. So it just sweat just pours straight off of a beer onto a coffee table. All the moisture in the air hits that cold beer, liquefies, and just drops down. Yes, so that is the same concept. We're dropping it below its dew point. So an oven is going to remain at a constant temperature. And when I say constant, these oven temperatures are within a 1 degree. they maintain a constant temperature. Another constant. GCs work off constant. We're going to have carrier gas coming in. Carrier gas on this case, it's going to come in on 3 and 6, and sample loop 2 to 9, sample in 1, out 10, same thing over to here. When we get our carrier gas set, and we have a flow that is going to be coming off of our thermistor beads of carrier gas, it's going to be constant. So let's say we're going to set this to 20 cc's a minute. Once it gets set to 20 cc's, we set this flow. We're going to have a reference. So carrier gas is going to come in, it's going to go across the reference, and that's going to go out. Reference against all the other beads, we're going to compare them, and we're going to get deeper and deeper into the TCD. But the main thing is that this flow is going to be a constant. And once we set this flow, and it is a constant, everyone will elute out at the same time, same back place, same back channel, every single time. Y'all don't know what that means, but back whenever there was Batman on TV, they'd say, come back next week for same back place, same back channel. So, yes, when we push these guys with carrier gas through these columns, and then they go across these beads, they're going to show up at the exact same spot, known as our retention time, every single time. Same spot, same place, every single time, every single time. And since it is going to be the same size sample that we're using, and so we're using a bottle to calibrate this thing, we're going to have the same size sample, which is our sample loop, and this is going to be 30 microliters. That's like a cube, microliters. We're going to have the same size sample, same flow rate, constant oven temperature, pushing everybody through these columns who is separating out the components where they elute, and they will show up at the exact same time every time. And we're using this bottle to calibrate this guy, so it's going to give us the area of these peaks. And once it gives us the area of these peaks, we tell it that this is 30, this is 40, and this is 30. And they add up to 100. But they show up at the same time every single time because GCs are built on constants.